Hello, everyone, and thank you for attending today's session. My name is Brett Purdy, and I'm the Executive Director for Environmental Innovation at Alberta Innovates and a former Director for the Water Innovation Program. So this is our 5th webinar in the Water Connect series, and Vicki, our current Program Director, has given me the opportunity to moderate today's session. So just to kick things off, I'd like to cover a few housekeeping items. At the bottom of your screen are engagement tools that you can use to support this particular webinar. All of these engagement tools are resizable and movable, so feel free to move them around to get the most out of your desktop. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner of each of the tools. If you have any questions during the webcast, you can submit them through the Q&A tool, and we will try to answer as many of the questions as we can at the end of the 3 presentations. There's a group chat box that is a useful tool to connect with other participants. So I'd encourage you to use it to discuss the session topic, but certainly don't let it distract you from the presentations. For the best viewing experience, we recommend closing any programs or browsers running in the background that can cause issues. You can find a few additional answers to some of the common technical issues located in the help tool at the bottom of your screen. So with that, I'd like to welcome everyone to the Alberta Innovates Water Innovation Connect series. And today's topic, Watershed Management, what we have learned and where we are going. Certainly what we do in our watersheds, whether it's protection, conservation, active management, and how they react to weather systems and changing climate can have big impacts on our water resources. At a landscape level, there's certainly the terrestrial interface that have strong influences on impacts of water supply, aquatic ecosystem health, and source water quality, all things that we invest in the Water Innovation Program. In our program, certainly a significant body of research has been underway for the last 10 plus years, and much more outside of it, trying to improve our understanding of cause and effect relationships in our watersheds. It's certainly an evolving theme in our program, and it's timely to reflect on what the research has told us and what and where we need to go from here. So today, we're lucky to have Rich Petrone from the University of Waterloo, Uldis Silins from the University of Alberta, and Chris Hopkinson from the University of Lethbridge join our webinar. So their bios are available in your engagement tools. For those of you not familiar, Alberta Innovates is a provincial corporation created to support research and innovation activities. We provide funding programs, advice, connections, technical expertise, and applied research services. Our scope encompasses the whole innovation journey from applied R&D through to commercialization of and end use of knowledge and technologies. So that includes science informing policy and practices, as well as technologies that get used by industry and others. So the Water Innovation Connect series will share ideas and outcomes from projects funded through our program, our Water Innovation Program, and in the future from those beyond it. The Water Innovation Program is designed to help and achieve the goals for the Alberta's Water for Life strategy and the Alberta Water Research and Innovation strategy. The knowledge and technologies developed in the program help to create a clean tech industry in water treatment, to support improvement in water use, conservation, efficiency, and productivity, and to provide safe, secure, and reliable water resources for a growing population while maintaining the health of aquatic ecosystems. So I hope the series and today's seminar will provide you with some valuable information and spark discussion. So with that, let's get started. I'm going to pass it over to Rich, and he'll take over for the first presentation. Rich Petrone will present on their findings on ecological controls on the hydrological response to climate change and extreme events in the Canadian Rockies. So over to you, Rich.
Great. Thanks, Brett. Thanks for coming, everyone. And just as you've introduced me, my printer decided to clean and calibrate, so hopefully it's not making too much noise in the background. But I'd like to take today to present a little bit about what our research group has been doing over the last few years with work largely funded by Alberta Innovates. So I'll be presenting work today on behalf of my colleagues on this project, John Pomeroy and Sherry Westbrook from the University of Saskatchewan, Misaki Hayashi from the University of Calgary, Bruce Davidson from Environment and Climate Change Canada, and John DeWoo from Alberta Agriculture and Forestry. So to start with, the consensus is that future climatic conditions are going to bring changing precipitation regimes and temperature regimes globally. This is well reported, and nowhere is this going to be more significant than in Alpine regions. Alpine watersheds are really the water towers of the world. For their relative global spatial coverage, they tend to receive and produce disproportionately more precipitation and runoff. So they're very important for providing water for downstream watersheds and communities. So the water balance of these watersheds is strongly controlled by the phase change of water in both precipitation and in storage of that water in these watersheds. So given these current climate change predictions, these watersheds are particularly vulnerable, both in terms of their respective eco-hydrological functioning, but also their downstream yield. So we really need to enhance our current observation networks in the mountains, learn more about the process hydrology, advance that knowledge of process hydrology, and improve our modeling to really understand this water supply resiliency and vulnerability. And after the first few years working in this area with my colleagues, we've come to the realization that we really need to focus on alpine wetland and forest ecohydrology and how these might be impacted by changes in things like forest cover, soil change, and climatic change. So we know this is particularly important in areas like southern Alberta, where basins like the Bow provide water for at least 3 provinces. The Bow River is also one of the most densely populated basins in Alberta, with, however, the least amount of water available per person. And areas of the upper Bow that were once relatively undisturbed are now being encroached more on by forestry, grazing, tourism, and recreation, and so on. So we have to understand how these different disturbance regimes might impact the water cycling in these alpine watersheds and also their yield. So just first consider the observations and management of these alpine watersheds in the context of climate change. So this pervasive warming that's predicted is going to change the precipitation regime of these plots. So this is a couple of images on this slide looking at forecast changes in temperature and precipitation over the next 60 years or so. So over that period, Western Alberta is expected to warm by 2 to 2.5 degrees, and much of the central portion of the Rockies is going to experience a decrease in precipitation, but much will experience a small increase. So these changes in precipitation are going to lead to things like changes in snowfall and rainfall regimes, decreasing snow cover depth, changes in the duration of snow cover season, retreating great glaciers, and warming and thawing permafrost. So as a result of these increased temperatures, we're going to significantly change the water balance potentially of these alpine watersheds. So we really need to understand what the watershed properties and processes are that respond to these types of changes. And we need to consider those in regional water and land use management plans. Sorry, my dog's outside the door, eagerly waiting to come back into her bed. That was her that you just heard sneeze. So what are the watershed processes and characteristics that we need to really examine now going forward and provide this sort of scientific foundation for alpine watershed management? So our work building on recent and ongoing enhanced mountain hydrometeorological observations and recent advances in cold region mountain hydrological modeling have led to some advances in our knowledge of the hydrological and the eco-hydrological functioning of these mountain watersheds. So some previous work by our group and others has demonstrated the need to acquire better physical understanding of the whole suite of mountain, wetland, and forest hydrological processes that control things like snowmelt, water storage, evapotranspiration, and runoff. So this is not only going to provide benchmarks in these processes that we can use to assess how they might change with disturbance or climatic variability, and the overall eco-hydrological behavior of these alpine watersheds. But we're also going to be able to incorporate these new advances from this improved understanding into hydrological models, especially hydrological models that focus on cold region processes, like the cold region hydrologic model, CRIM, and MESH. So our next phase of this Alberta innovation-funded work is to start to ramp up the modeling, especially at the scale of mesh and so on. So we really want to be able to start to explore the water storage roles of wetlands, for example, and how this might change and what the downstream effects might be of such change. Also, what the hydrologic impact of current and scenario forest covers, soil disturbances, and changing mountain forest snow interactions due to land use change or climate, and what effect that might have on other land cover units in these watersheds like wetlands, and again, also what it might have on the overall yield of these watersheds. So by doing this, we should be able to establish climate and land cover change tipping points that we might be able to better quantify the resiliency of these alpine water supplies. So what processes are we going to focus on? So using a combination of field-based measurements, using extensive network of sites already established in the more the southeastern Rockies, in the Kananaskis and Banff areas. Also combining that with remote sensing and modeling tools, we're going to work to quantify the relative importance of biophysical and meteorological variables on forest and wetland ecohydrology and how they might vary along an elevational gradient. So we can see just the example here, this sort of conceptual diagram of some of the biological and physical factors that control evapotranspiration, which we know is an important component of the water balance, can be very complex in alpine environments. So I'll go over some of the results of this work so far and just highlight some of the key findings. So the first bit of findings I'd like to go over is that of the groundwater and surface water work. And this is led by Misaki Hayashi and his group at the University of Calgary. So how these watersheds are going to respond to changes in precipitation is to a large degree dependent on the groundwater dynamics and connectivity of that groundwater with surface water, and wetlands especially. But I'll get more into that in a little bit. So for example, the base flow of eastern slope rivers like the North Saskatchewan, South Saskatchewan, Athabasca is important for water supply for at least 6 months of the year. So we can see the diagram on the left here, which just shows the North Saskatchewan River hydrograph. And we can see that over at least half of the year, base flow is almost completely sustained by groundwater. And much of that comes from alpine headwaters. So focusing on trying to understand where these alpine aquifers are in these headwater watersheds, looked at hundreds of alpine aquifers and headwater basins collectively, which provide groundwater inputs to these alpine rivers. And Misaki's group has advanced our understanding of these alpine aquifers, the moraine, talus, and rock glacier systems, to the point where we're really starting to build simple mathematical models representing these aquifers into things like CRIM. So this is going to improve the groundwater component of some of these cold region hydrologic models and other surface schemes, but also will improve our river hydrology models. And using these sorts of tools are going to be important for developing water resource management plans under future warmer climates. So in the groundwater theme of our work, Misaki's group is now working on characterizing the function of these alpine groundwater systems and regulating the flow and temperature of headwater streams and how that might buffer the effects of climate warming and also act to stabilize stream base flow. So previous studies in the Rockies and around the world have really established that these are facts, right, that they can behave in these systems, these alpine aquifers. But there are new questions now that he's exploring in this project, and we'll go over the points that we're looking at now. So some of the new questions that have emerged are, what are the types of aquifers that are prevalent in the eastern slopes of the Rockies? How do they regulate stream base flow, and how do they regulate stream temperature? So they focused this research and trying to address these questions largely in the Fortress Mountain ski area. So this represents typical conditions of the eastern slopes, consists of complex alpine landforms such as talus, moraines, and alpine meadows. The photo on the left. He's done extensive geophysical imaging and groundwater monitoring in this area over the last few years, and has found that groundwater discharge at outlet springs feeding the first order streams is essentially controlled by moraines at the end of the system. So these moraines and these sorts of alpine watersheds act as gatekeepers for that watershed, really controlling the quantity of water that gets out, but also sort of the characteristics or the conditions of that water that's released into the streams. So looking at this example from Fortress Mountain, we can see that the landscape features in this infrared image that we had in the previous conceptual diagram on the last slide are located in this image. So we have the meadow wetland sort of in the upper left, talus slope in the upper middle, this meadow wetland area also on the middle right, and then right where that red oval is this sort of seasonal ephemeral lake. So there's 3 distinct discharge points in this particular catchment that are denoted by the S's and the numbers. So S1 is the discharge area from that seasonal lake, whereas S2 and S3 are direct discharges from the meadow wetland and the talus slopes, respectively. So during the summer months, we can see in this image that the temperature of the discharge point S1, the one that's coming out of the lake, is much warmer than those coming out of the wetland, meadow, and talus. So we'll look at what the conceptual framework now is that's derived from these findings so far. So his results so far are suggesting that there are at least 2 pathways of groundwater through these gatekeeper moraines. So the pathway that feeds points like S1 in the previous slide are influenced by the warmer lake water, right? Even these shallow seasonal lakes absorb a lot of energy during that very brief summer period, so that water tends to be a lot warmer. The pathways, though, feeding the S2 and S3 discharge points bypass that lake. So we typically see these happen later in the season when that seasonal lake water level drops or the lake completely dries up. So climate warming will likely result in earlier snowmelt and therefore a likely earlier drying of that seasonal lake or seasonal lakes like that, making the main pathway then for discharge to streams like this through the colder pathways and not through the warmer lake. So this might actually lower the temperature of groundwater discharge at springs like this and lower the stream temperature in summers. So climate warming might actually result in some cooling of stream water and may have implications in the maintenance of cold water habitats in these areas under a warming climate. So the other main focus of our work has been and continues to be sort of the role of vegetation change, vegetation distribution and dynamics, because these are features of these watersheds that use a lot of the water that we're talking about and control these interactions between groundwater, surface water, and precipitation. So we really focus on 3 aspects of vegetation in our alpine watersheds: tree line migration, wetland ecohydrology, and forest water use. So in terms of tree line migration, it's been well documented in other alpine areas that as precipitation regimes change, it's going to influence the elevational gradients and moisture availability. As temperature regime changes, it will expand the range of suitable climatic conditions. So both of these are going to expand the range of existing vegetation communities. It's generally going to expand upward in elevation. So this is just an example on the left here from some of John Pomeroy's work in the Yukon, and showing pretty clear rapid shrubification of these areas that were once above tree line. So this expansion is going to change the overall water use in these alpine watersheds, therefore affecting their overall yield downstream. In terms of wetland ecohydrology, we know that mountain wetlands and peatlands possess both auto and exogenic ecohydrological feedbacks that maintain their required wet conditions. But their heavy reliance on these external controls make them sensitive to surrounding land use at a range of scales. So at the local scale and also at the watershed scale and beyond, if these hydrologic connections to the wetlands are disturbed or altered, it can affect the water balance and functioning of these wetlands. So we know wetlands are important because there's significant water stores in these watersheds. And we found, as the figure in the top of the wetland box on the slide shows, this is work by Sherry Westbrook, that their water table really depends on snowpack amount and not so much snowmelt timing. So we can see water table depth increases as our depth of snow before the melt period increases. So it's not so much when melt occurs, but how much snow there is to melt. They also receive significant water stores, water transport from the adjacent upland areas, the adjacent slopes. So as I said earlier, they're also going to be sensitive to any disruption in those slopes that might affect those flow paths. So changes in climate might impact the snow inputs. Upslope disturbance like clear cutting, roads, trails, etc., may impact these other primary hydrologic inputs. Then there's also beaver. So a lot of work Sherry's group is doing now in this project is looking at how beaver impacts are affecting storage and flow from these wetlands. And then finally, we're looking at forest water use. So since the forests in these alpine areas really account for the most biomass and therefore probably the most water use, they're an important consideration for us. So understanding where these forests get their water and when and how efficiently they use it is going to be very important to the overall watershed water balance and also the water yield downstream. So the plot on the right just simply shows, this is sap flow measurements of transpiration from some forest stands in Fortress Mountain, just shows the significant amount of water a tree in these alpine forests can use over the course of the day and just how that varies over the course of the season. But we've also been looking at the isotopic signature of water in these tree tissues relative to the isotopic signature of some of the potential water sources. So the plot on the left there just shows the isotopic signature of this plant tissue water relative to the main sources. So the light band across the top of the figure is the seasonal range in deuterium values for soil water. So that's just the water that's held relatively loosely in the shallower soil pores. The dark band at the bottom is the isotopic signature for groundwater. And the band in the middle is really the crossover range in soil water, groundwater values. So what we did was look at these isotopic signatures over 3 periods of the snow-free season. So the pre-period is that period right around snowmelt. We can see that trees are using more of the available groundwater, right? And that's water that's been recharged by the recent snowmelt. The middle period, which is sort of the peak growing season in these systems, the trees are using more soil water that they can reach that's available to them. And then in the end period, this is sort of later going into the senescence period, August, September, the trees are using soil water, but now we're also seeing the influence of that sort of late season precipitation, especially in the form of snow after the drier summer period. And we've also distinguished between size class in that figure as well, between small and large trees. And we can see that the smaller trees tend to favor soil water as opposed to the larger trees using more of that deeper infiltrated water. And it makes sense the function really of their roots. And just really quickly, want to touch on some of the scaling work we're now doing with this vegetation work, where we're conducting measurements on water use, carbon uptake at the plant community and individual plant scale, and then using tools like drone-based imagery to scale up this to the land cover unit and watershed scale. So using things like chlorophyll, coloration to detect and quantify the productivity of some of these vegetation communities, and then infrared estimates of plant temperature to quantify and scale the transport of losses. So we can start to, at fairly large scales, once we refine these models based on the drone-based imagery, pretty quick, large-scale estimates of water use efficiency in some of these different alpine communities. And this is so far talking a lot about our understanding of current processes as a means of feeding our models to come up with future forecasts. But one way we can also improve our understanding is by looking at how these systems behaved in the past. And some members of our team are now looking at using wood anatomy to reconstruct things like water use efficiency and productivity in the past, where we can look at how these systems have responded to climate change, but we can also look at how they've responded to development and disturbance as well. I won't spend too much time on that, but I'd be happy to answer any questions related to those last 2 slides. So I just want to summarize now a lot of the modeling work that's been done and is continuing to be done by John Pomeroy and Bruce Davidson, largely in our group. So far, their efforts have focused on improving our process understanding of things like glaciers, avalanches, discontinuous forests, energy budgets, forest and wetland, evapotranspiration, groundwater, and snow processes like especially redistribution and ablation. And looking at what the relative importances of these different suites of processes in our modeling of these mountain systems. So this is going to be useful for headwater and river basin scale tests of climatic and disturbance regimes. So the two figures on the left-hand side of the slide here are just showing some examples that they've run using CRIM for the Bow River at Banff. So based on about 2,800 hydrologic response units, just tested how well CRIM could simulate the discharge of the Bow at Banff. And we can see there's pretty good agreement between the modeled and measured discharge. The example on the right, using the same model setup, but now taking the conditions for the 2013 flood period and looking at how the hydroclimatic conditions of that year might interact with other disturbance features. So if we have sort of the similar hydroclimatic stars line up in the future, but now we've got other disturbance effects piled on top of that, what might be the effects? So they tested things like different types of fire severity, high intensity, very severe fires to low intensity, not as severe, different types of harvesting practices, and even insect infestations. And what the results of that run show that severe fire coupled with the climatic conditions and antecedent conditions we had in 2013 could lead to 3 times the flood magnitude at Calgary. So they're now expanding this sort of work to run similar analysis at larger watershed scales by implementing a lot of what we've learned, implemented and tested into CRIM into the larger mesh model, hopefully to improve our operational forecasting of ungauged headwater basins. So we can start to look at things like glacial retreat, land cover change, and so on, and what the effects are on downstream water supply at larger scales. So just a couple of other interesting examples that have come out of some of the modeling experiments. So far, they did another experiment to look at how snowpack might change in a changing climate and what the effects might be on yield. So using the Marmot Creek Basin with the extensive data record that they have there, looked at how that might change under changing climate. So again, running the cold region hydrologic model, driven with climate inputs from WRF at 4-kilometer resolution. So they ran it for sort of the normal scenario and then with the pseudo-global warming scenario with a warming of 4.7 degrees and an increase in precipitation of 16%. So they ran it for the main land cover types in Marmot Creek. So we can see those in the 8 panels here. And what the modeling has shown is that there's really no significant change in snow accumulation at the higher elevations, like the Alpine sites and the upper forest, so panels A and C in the figure here. And there's less snow and an earlier melt at the lower elevations that we see in the tree-lined forest panel and the different lower forests. And this earlier melt is exacerbated by forest harvesting. So if we look at the clear-cut examples there. So overall, on average, about a decrease in 84 millimeters of snowmelt volume. So what does this translate to then in terms of yield out of a basin like Marmot? So that same change in snow accumulation has led to an 18% increase in discharge, but which comes about 45 days sooner. So there are going to be clear impacts on water yield and potentially downstream water use under changing climatic conditions such as these. So to summarize what we've been learning so far in our work here in this Alpine watershed science and where we're going and what the implications might be for forest management, we're working at and have made progress in improving our understanding of mountain hydrological function, as well as establishing benchmarks for assessment of how resilient these water supply systems might be and maybe what the resulting ecological feedbacks or change might be. The hydrological data sets and models are proving to be useful to study the effects of climate variability or change, as well as anthropogenic disturbance on southern Alberta's water supply. So we're hoping what will come out of this then, and will continue to evolve and improve, are better information tools and techniques to manage the uncertain water futures in the Rockies and help to develop transformative decision-making tools that various levels of government and province and beyond can use to manage their water. And just some of the where we link in with some of AEP's science strategy priorities and so on. So I think I'll leave it there, but again, happy to discuss any of this further in the question period. Just want to acknowledge, obviously, Alberta Innovates, who's funded the bulk of this work, but also we've leveraged that with some of our other partners with the Alberta government and CERC, Spray Lake Sawmills, and the Global Water Futures Program. Thanks.
All right, thank you, Rich. I'll just hand it right over to Uldis next. And so Uldis Silins is going to speak on, let me just pull up the title here, The Future of Water Supply and Watershed Management in Alberta, Best Source to Tap Practices from Source Water Protection in the Eastern Slope. So Uldis, unmute yourself and you can take over from here.
Okay, thank you very much, Brett. And thank you very much for the invitation to speak to you all today. I guess I should advance the slides. So as Brett indicated, I'm going to be speaking about a historic project that that just wrapped up last year, but the work is continuing. And so really I want to take this opportunity to frame some of our higher level or strategic insights that have been emerging from that historic work and the ongoing work, the ongoing line of water research. So to begin, I need to acknowledge this work is being done by a very large integrated team of water scientists. So I need to acknowledge the many, many team members that have contributed to this work. I'm just the front man here that's telling the story. So the focus of this work has been on many of the themes, really building on the themes that Rich had talked about, climate change and extreme events. The context for this work is focused on protecting source waters in critical supply regions like the Rocky Mountain East Slopes. Lots of conversations in the last decade, particularly with Land Use Framework and the Sustainability Act. And really, when it comes to source water protection, the dominant narrative, and it's the historic narrative, is that source waters are best protected by preventing deterioration of water, best protected by preventing land disturbance. But climate change, many of those things that Rich was talking about, an intensification of weather in particular over the last 20 years has been steadily increasing the potential for some of those severe, even catastrophic impacts on water. Wildfire in particular, Rich touched on wildfire. And historically, while wildfires are an important component part of our fire-adapted ecosystems, I think we are all inundated by both news, local news, national news, international news, and our own experience with wildfire smoke. So more recently, this has become kind of stunningly commonplace. So our more recent experience with wildfire is far beyond anything that we thought sort of historic. So fire-prone regions really are experiencing more frequent, large, severe wildfires. And some of our past work has shown that the impacts of those wildfires to water supplies can be exceedingly large and long-lasting in regions like Alberta. And while little can practically be done to manage some of the weather conditions that are driving those fire disturbances, the project here is really focused on, to what extent or what role can contemporary forest management strategies play in active integrated source water strategies, or in fact, do their potential benefits outweigh the potential or the potential impacts outweigh any of those potential benefits? So since 2004. The Southern Rockies Watershed Project Observatory has been documenting both severe climate disturbances like wildfire, but it's been running for long enough that we have observed a number of these climate-associated disturbances, including the very severe 2013 flood that affected the city of Calgary. But then also really taking the opportunity to study, well, what are the impacts of land management activities, both historic harvesting practices and more contemporary harvesting practices. So the research has really grown to encompass 36 large, historic, and currently instrumented watersheds. And so this is probably the only large-scale watershed observatory of its kind worldwide to specifically focus on observations of those natural and anthropogenic disturbances. But perhaps most notably, the most unique part, I think, of this project is really the focus on a broad cross-section of water resources values. So really that work is linking a whole bunch of attributes of headwaters hydrology, water quality, their subsequent impacts on stream health, to what does that look like for downstream effects? How are those effects propagated downstream? And then considering what are the impact on communities, principally focused on drinking water, and including economic evaluation of some of those. So many people talk about source to tap, but this is truly difficult to evaluate because it necessarily requires a transdisciplinary approach that really spans those highly diverse science, engineering, and management and policy domains. So I'm going to focus today more on the watershed impacts, but I want to put a plug out the Monica Melko, who's a co-PI on this project, also leads an allied project focused on drinking water, and there's going to be a seminar in this seminar series on November 8th that's going to focus very specifically on wildfire and drinking water threats. So if you want to hear more about that, that will be a really good seminar to take in next week. So planning for this study, really looking at contemporary management practices, there's a lot of work has been done on historic management practices, and the narrative is, I think, a pretty common one, that forestry practices have been historically hard on water. Comparatively less work done on more contemporary practices because they have changed. And so the focus here was really to evaluate a number of different alternative contemporary practices. And so this work, planning for this work began many, many years ago. It was harvested by CANFOR in 2015 and really included a very broad group of erosion control measurements, or erosion control measures and best management practices to minimize impacts on water. Later on, roads and everything were decommissioned. And it's probably notable to mention that watershed studies of this kind can't be done quickly because disturbance effects on water really vary from year to year with different kinds of weather conditions from year to year. And so the really powerful approach, having pre-disturbance data from the previous wildfire work, allows us to really disentangle some of those disturbance effects cleanly from effects that are produced by variation in weather. And so last year was the fourth full year after harvesting. And so it's important to mention we're doing catchment scale work to look at the ultimate outcome of those different disturbances on various aspects of water. But that needs to be coupled with process work that provides the insight into why do we see those effects. And so we've got a large number of graduate student projects that are focused on everything from snowpacks and evaporative demand and tree water use and surface water, groundwater interactions. Lots of work at hill slope and plot scales on nutrients, erosion, movement of sediment, and then, at larger river basin scales, looking at what are the consequences in the larger river systems, receiving waters, and in fact, what are the implications for water treatment and drinking water. So here I'm just going to give you a very high-level snapshot of some of the catchment scale results that we've seen. And we've seen some pretty surprising results. And these results are not, in fact, consistent with some of the common narratives that, you might see in the scientific literature or perhaps publicly held narratives on how forest harvesting, logging impacts water quality. So here you're looking at an example. This is just focused on sediment production. And so these data, and this is really the power of this before-after control impact study design. What you're looking at here is the relationship between sediment production, it's flow-weighted sediment production, so it's sediment yield, between logged and unlogged watersheds before the watersheds were logged. So on the x-axis, you've got sediment production, of course, from very low levels to very high levels, and then the corresponding sediment production in the harvested watersheds prior to the imposition of harvesting. So in 2015, those areas were logged. And so here you're looking now at 4 years, 5 years total, but 4 years of post-logging data. And what you can see is relative to that pre-disturbance relationship between sediment production between the control and treated watersheds, you can see that after harvesting, the sediment production actually went down. So those orange dots are all sitting below the green dots. So that indicates that not only was there no increase in sediment production, not only was there no change, there was in fact a change. Sediment production went down. So this is a really highly contrary finding to the kind of common narratives that we see. So that data that I showed you was from the clear-cut harvested watershed, and this is about a 4 square kilometer watershed. 3 other watersheds that were harvested with different kinds of alternate practices, strip shelterwood harvested watershed, and then one with partial cut harvested watersheds. Well, there's variation in how things changed. In every case, what you see is the sediment production actually went down after harvesting. And so we see similar kinds of effects on nutrients, nitrogen, phosphorus, organic carbon, many of those water quality parameters that we consider important. And in fact, the evaluation of impacts on drinking water treatability showed that there was no effect. So we did, however, see, and it looks like we're seeing an effect on flow, and that work is still ongoing to really nail that down. But big picture, really what that suggests is this broad suite of best management practices that were employed in this case have been highly effective, not only at minimizing those impacts, but in fact eliminating those impacts. The corollary here is and it's bizarre, is that water quality actually improved after that harvesting. So here, looking at the larger project, we very much, if you look at the map on the left, you're looking at the different harvested units, clear cut on the left, strip cut in the center, and partial cut on the right-hand side. We certainly expected to see a different response between those 3. So we expected to see larger effects perhaps in watersheds that were more heavily impacted. However, the corollary is when you move to partial cut harvesting systems, you need to have a higher road density. And so while a clear-cut harvest may have a higher intensity of a footprint, there's only one road in and one road out. And we do know that that roads can produce a lot of those impacts. So we also expected, well, maybe the road density would have actually turned those results around. But in fact, what we saw is all 3 of those study watersheds, sediment production and water quality impacts were actually non-existent. In fact, water quality improved. So we're left with this conundrum. Well, how do we interpret this result? Because then we're left with saying, well, where did water quality improve the least? So in a way, it really is a bit of a confusing result. However, I want to take this opportunity to, because of the different kinds of disturbances that we studied, I want to take this opportunity to take the helicopter up to 40,000 feet and just say, okay, what do these different land disturbances really mean to water? So what is source water? What are these source water threats in a warming sort of warming landscape? And so the question is, how do you represent those impacts to water? What is the currency? Is it flow? Is it water quality? Is it impacts on ecosystems? So in this particular case, I'm going to focus on 3 particular parameters. So here we're looking at phosphorus, sediment, and organic carbon. And it is the yield, the flow-weighted production of those. So it necessarily integrates both changes in flow and changes in concentration of those. And really collectively, those three become almost parsimonious or proxy indicators for broader impacts on aquatic ecosystem health, on human uses of water like drinking water, because all three of these parameters really govern some of those impacts. So what I'm showing you here is a comparative snapshot of these different kinds of disturbances over a prolonged 2-year period. So you're looking at average production of sediment, phosphorus, and organic carbon over a prolonged 2-year period. And what you can see here in this graph, we've got sediment production on the top graph, phosphorus on the second graph down, and then carbon production on the lower one. And here we're comparing a number of different kinds of disturbances. So on the left-hand side, we're looking at natural disturbances, so flooding in particular. The 2013 flood was a major channel modifying flood in this particular region. And what you can see is flooding is exceedingly hard on sediment production. The reference watersheds beside each of those, there's a number of different reference watersheds that are used here to sort of compare. We have reference watersheds. So what we're comparing here is undisturbed watersheds before the flooding to those same watersheds after the flooding. And what you can see is flooding is exceedingly hard on sediment. Going down, it's pretty darn hard on phosphorus, which really drives some of those ecosystem effects and effects on drinking water. But it doesn't have a lot of impact on carbon. By contrast, the 2013 wildfire, wildfires produce a lot of sediment. And we've also got the 2017 Keno Mountain wildfire in here. And so one of the points is that all of these fires are very different. And we're learning that you can't just study one fire. There's many, many different kinds of effects that are sort of emergent. But what you can see is wildfire very, very hard on sediment, really hard on phosphorus, and pretty darn hard on carbon. And by comparison, if we're looking at some of these anthropogenic disturbances, we saw some rather disturbing legacy effects from historic harvesting 20 years ago and 40 years ago still evident, most specifically with organic carbon. But then if we start to look at the more contemporary practices, we're looking, well, all of these actually, these impacts were actually less. But the big picture here is this comparison between these severe natural disturbances, wildfire and flooding, even though they're totally different. One's a banana, one's a potato, compared to anthropogenic disturbances. Rich indicated, and he showed an example of compound disturbances. So as as weather continues to intensify, the likelihood of having intersecting natural disturbances becomes higher. And so in this particular case, we might consider salvage logging, here the next group of bars, as an example of a compound natural and anthropogenic disturbance. But then the flooding, because we have a 9-year period of studying the fire after the fire and salvage logging after the Lost Creek fire, and then studying the impacts of the flood on top of that. And what we can see is those compound disturbances, even a decade after the fire, produced almost an order of magnitude higher impact. So these compound disturbances that Rich alluded to, we actually measured these and documented these, and those impacts are exceedingly high. So big picture, what do we know? In keeping with the context of, or the theme of this workshop, what we know, and we've known for some time, is that these climate-associated disturbances, natural disturbances, produce the greatest impacts to source water supplies by far. Wildfire is about the hardest thing we can possibly do to water. And unlike the stupid times that we're living in right now with COVID and trying to figure out what does our future look like, the one thing we know is that the inertia of the climate change we've already seen is likely to continue to force increases in those natural disturbances for decades to come, even if we completely eliminated use of fossil fuels. The other big picture take-home message here is that contemporary management practices, unlike those common narratives, can actually produce minimal to even no impacts on water. So that really changes the conversation and changes the focus, the management focus from or to really a focus on those best management practices. So the operating ground rules and really minimizing those impacts. This work doesn't necessarily reflect the broader application of that across the province, but what the work does show is judicious application of those best practices can not only minimize or eliminate those impacts, but in fact, as we saw, water quality actually paradoxically even improved after harvesting. So this really speaks to the broader paradox that we have, that in the face of a changing, shifting climate and some of those climate-associated threats, that forest management is really well aligned with some of those broader source water protection objectives. And I will just jump through this and just where are we going? Well, where we're going is there's still a lot of things that we're finding out. Wildfire, there's many things that are just emerging, and so really the scope of those impacts still are not very well understood. And then some of the broader issues tied into sort of the management end. We are also part of we've initiated a much broader national network looking at forest management practices across the country. And so some of the big themes there are, what really are the options in terms of climate change adapted silvicultural systems, what can be done in terms of managing landscape resistance, resilience, really to achieve some of those source water protection objectives. And I'll just finish up here. Lastly, it's really important. I need to thank our broad list of agencies that have really supported this work. And I'm going to leave that there and follow back and address some questions potentially in the question and answer session.
Okay, thank you, Uldis. I'm going to pass it over to Chris now, and Chris is going to lead off with a presentation that's going to focus on the Castle Watershed, a new water resource assessment framework for a Sentinel system in the crown of the continent. And Chris is here with us today, but he developed a pre-recorded message that allowed a consolidation of video and other materials together. So I'm just going to forward it for him, and then we'll kick off with a video presentation that will then circle around back to have a Q&A with all the presenters.
Hi, I'm Chris Hopkinson, Professor of Geography and Environment at the University of Lethbridge. Today, I'm going to talk about our innovations in environmental monitoring in the headwaters of the Oldman River Basin. Here we see the location and outline of the Oldman Drainage Basin upstream of Lethbridge, with 5 of our airborne LiDAR monitoring sites outlined. The Headwater region is where most of our water originates as snowpack, which typically melts off over a prolonged period due to the elevation range and forest cover in the mountains. For the Water Innovation Program, most of our activities have centered on the West Castle watershed, where we have an established field station, field plots, and telemetered hydrometeorological instruments, all of which are also supporting our airborne multispectral laser scanning research and monitoring. Here we are at the University of Lethbridge West Castle Field Station, which is where much of the work I'll showcase today has taken place, or started. Through the Water Innovation Program, my grad students and I have developed and tested innovative LiDAR, LiDAR, and photogrammetric techniques to evaluate long-term forest vegetation changes or to monitor winter snowpack across the entire West Castle watershed. The techniques we have developed have integrated field plots, weather station data, and LED-based ranging, as well as remote sensing imagery to deliver a comprehensive understanding of watershed dynamics across seasons and over decades. Over the next 20 minutes, my students and I will share with you some of the developments from the work in the castle, and as well, we will illustrate how we are building on what has been learned to study the impacts of the Keno wildfire on vegetation recovery and montane water resources. And finally, I will end with some thoughts on our vision to utilize this framework in a community-based monitoring context. First, we'll examine some remote sensing innovations in forest mapping and monitoring undertaken by Maxim, Thomas, and Dave. Second, we will explore Kelsey and Celeste's innovative research into snowpack monitoring and modeling using LiDAR and LED ranging. Then, we shift location to Waterton Lakes National Park, where Jesse and Travis are tracking the early stages of forest ecosystem recovery following the Keno wildfire of 2017. And finally, we travel slightly downstream to join Danica as she explores the co-creation of knowledge using LiDAR and indigenous wisdom with Piikani First Nation. Given LiDAR plays a prominent role in my lab, we start with Maxim for a summary of our recent multispectral LiDAR research.
I have flown and processed multiple LiDAR datasets over Castle and Waterton. The summertime surveys provide a baseline DEM for snow mapping as well as information about vegetation change in the headwaters. In 2016, I designed and installed radiometric calibration targets to calibrate multispectral LiDAR intensities and derive reflectance values to help characterize vegetation in the West Castle.
Multispectral LiDAR is just like regular airborne LiDAR in that we can derive terrain and canopy height or canopy cover models, but due to operating at 3 different wavelengths, we can also generate colorized 3D imagery. And as an example, here we see a 3D laser composite image of the Wapta ice fields in the headwaters of the Bow River. Such images may be impressive, but as this is a new remote sensing technology, there are no standard calibration routines to provide actual laser reflectance. Furthermore, channel intensities can be ratioed to provide vegetation indices, but early experiments have demonstrated that such indices could vary with flying height or terrain elevation. Using accurately surveyed and spectrally calibrated 3-dimensional targets, Maxim devised a routine to radiometrically correct the 3-channel intensities and thus mitigate altitude effects and therefore derive new multispectral LiDAR vegetation indices. Taking this to the 3-dimensional realm allows us to compare the distribution of canopy spectral properties within the vertical canopy profile. As each wavelength responds differently over leafy and woody biomass, we can once again ratio the channel intensities to provide a cross-section or voxel-based vegetation index. Now, all of this may sound esoteric, but the real value in these 3D spectral data is that we can derive structural and spectral signatures of land cover types, including vegetation species, and therefore, using a single sensor, generate a high-resolution and high-accuracy feature classification map. So, let's change scales now and check in with Thomas to see some of his innovations in UAV monitoring.
My studies involved using time series UAV ortho imagery and structure from motion point clouds. We use these to track montane forest ecosystem changes in the Castle and Waterton headwaters. In Castle, we were monitoring trail restoration, while in Waterton, we were tracking early stage seasonal recovery of forest ecosystems following the Keno wildfire of 2017. These UAV images and models provide an invaluable archive documenting the regeneration of forest ecosystems after disturbance.
Here we see Thomas piloting his UAV over a trailhead in the Castle during a trail disturbance recovery survey. Instead of Castle, however, I will summarize some of the UAV post-fire recovery monitoring efforts in the nearby Cameron Valley of the Waterton Lakes National Park. The image at right illustrates the extent of severe wildfire forest loss in the Cameron Valley, and at left you can see one of the early UAV ortho images captured in spring after the Keno fire. Note the highlighted low-lying areas where snow accumulates and how these areas approximately correspond with new vegetation growth during the summer. See how a UAV greenness difference image clearly delineates these areas of new growth. Also, using artificial intelligence algorithms in the Picterra software platform, it is possible to identify and extract individual down stems. Of course, a benefit of UAV data is the ability to construct 3-dimensional point clouds using structure from motion. Here, the post-fire landscape dynamics are clearly visible in this comparison of SFM surfaces from 2018 to 2019. Morphological changes due to vegetation growth, downstem movement, and terrain erosion can be easily discerned. So let's check in with Dave now to examine forest cover changes over a much longer timescale.
I studied a century of land cover change in the West Castle watershed using LiDAR and repeat photography. Land cover is an important input into hydrologic models. Using machine learning techniques, I found that change in land cover in the Alpine tree line ecotone was primarily driven by aspect-specific patterns of regrowth after high elevation forest fire.
Dave used the University of Victoria Mountain Legacy Project image archive for Westcastle to document forest changes from 1914 to 2006. A wildfire passed through the castle in 1936, so some changes are due to this fire, such as the tree line reduction here, and some are due to more gradual successional or mortality processes. To convert these oblique photos into ortho images, Dave used the airborne LiDAR to create an accurate surface upon which they could be draped and manually classified into zones of forest cover. From the draped forest cover images, a change classification was derived for about 40% of the watershed. Stratifying by elevation shows that losses to tree cover are greatest near tree line, but there is also evidence of tree line advance into the Alpine zone. Examining the aspect influence shows a clear tendency for forest cover loss on south slopes and new growth on north slopes. To use these change data in further analyses required that we gap fill the 60% of the watershed that was not observed in the Mountain Legacy Project archive. This was achieved using a random forest model trained with the observed changes and driven by 9 terrain, land cover, and climatological predictor data layers. Combining the observed and simulated change products provides a spatially continuous map of century-scale forest change for use in further hydroecological or climatological studies. Now to a critical resource for those of us here in southern Alberta, one that varies quickly in space and time. We'll start part 2 with Kelsey to explore innovations in snowpack monitoring.
My research explored LiDAR snow depth modeling and quality control in the castle. Sensitivity analyses under midwinter and melt onset conditions confirmed well-known snow depth distribution trends, as well as the utility of LiDAR for seasonal snow mapping. I also employed machine learning to see if watershed scale snow depths could be simulated and dominant snow depth drivers identified. We hope this work provides a basis for future headwater snowpack monitoring in Alberta.
Multiple LiDAR snow depth models collected over Westcastle since 2014 were divided into midwinter and early ablation periods to evaluate the consistency of depth drivers at the 100 km² watershed scale. A random forest machine learning routine was set up both to assess the efficacy of operational snow depth simulation and to check whether the order of driver importance varied from the accumulation to the ablation periods. Despite the obvious depth variations between mid and late winter, elevation was consistently the dominant control at the watershed scale, with maximum depths occurring in the tree line zone between about 1900 and 2200 meters above sea level. Indeed, the data suggest tree line acts like a pivot point such that depth accumulates quickly in this zone and persists with limited variation while valley snow melts out and alpine snow continues to accumulate. The random forest analysis suggested that depth drivers were consistent across winter, with the order of importance descending from elevation to aspect to canopy to terrain morphology. The deepest snowpacks tend to occur in canopy openings on the north slopes at tree line, while the shallowest depths occurred on south slopes or under dense canopy. So now we know more about snow depth controls in the headwaters of the Oldman, let's check in with Celeste to see how watershed snow mapping can be operationalized.
My research is to map snow water equivalent using in situ LED and airborne LiDAR snow depth combined with snowpack density modeled from weather station data. To operationalize this framework, I am developing an airborne sampling and machine learning procedure that scales up to entire watersheds. This framework will create spatially explicit estimates of SWE for input into operational hydrologic models.
We've seen from Kelsey's work that LiDAR snow depth mapping works for a 20-kilometer-long watershed, but the eastern slopes of Alberta span around 700 kilometers, with about 200 of that draining into the Oldman. So the challenge then is to devise a snow mapping framework that can be scaled up to all eastern slopes headwaters. The obvious strategy is to use sampling, such that for the time it would take to survey the Westcastle, we might cover the entire Oldman headwaters. To test this approach, Celeste has designed sample flight lines across the Westcastle using a least cost path analysis to cover most of the dominant snow depth driver classes. Then, using random forest imputation, snow depth for the remaining watershed area can be imputed. Initial results are encouraging, with watershed scale test data producing an R-squared of 0.66 and RMSE of around 3 centimeters. To convert depth to snow water equivalent, or SWE, Celeste is using our elevation and spatial distributed weather station network in the castle to devise a watershed scale density model. This is a work in progress, but as part of this framework, Celeste has also built and tested a prototype LED snow depth profiling sensor. The LED ranger has 16 beams and has been co-located with other depth and energy balance sensors throughout 2 winter seasons. Results match or exceed the accuracy of similar depth sensors, but also provide snow texture and surface intensity. A next step is to explore possible commercialization. Now that we have a sense of the techniques we're employing for headwater monitoring, let's go to part 3, where we'll hear from Travis and Jesse and their research into eco-hydrological feedbacks following Montane wildfire. But first, a few words from Laura.
Here we are at one of our vegetation plots in the Acamina Valley. What we're particularly interested in is regenerating vegetation, especially pine.
My thesis builds on the snowpack and treeline research carried out by Kelsey, David, and Celeste in the West Castle. I'm using airborne LiDAR to study the impacts of vegetation recovery on montane hydrology following the 2017 Keno wildfire in Waterson Lakes National Park. This work will create a model of forest regeneration and snowpack feedbacks to help with water resource forecasting throughout the Old Man watershed.
As with West Castle, we are flying multispectral LiDAR over the slightly smaller Cameron Valley directly upstream of the Wardston town site to monitor forestry ecosystem change. Since the Keno fire in September 2017, we have flown 1 winter and 1 midsummer survey each year to track changes in terrain surface, standing dead trees, new growth, and snowpack distributions. As the burn severity map shows, we chose the Cameron Valley as almost all the vegetation and organic soil was lost, and the ecosystem must now re-establish. From the observations in Dave and Kelsey's work, we derive a conceptual understanding of the Cameron Valley hillslope snow and forest cover, such that under a mature forest scenario, snow depth peaks at high elevation tree line and plays a role in providing meltwater nourishment through the growing season. When the forest is removed by fire, we expect the zone of peak snow depth to move downslope, but the piece we wish to explore is how snow accumulation and tree cover interact during the tree line recovery phase. It's still early days in Travis's PhD research, but using the multispectral LiDAR, we will track biomass growth progression upslopes for the first 5 years post-fire and attempt to identify the snowpack to regeneration feedbacks and their variation with elevation and slope aspect. Continuing the theme of post-fire hydroecological interactions, let's check in with Jesse now to learn about his work along the Cameron Valley floor.
I'm using multispectral LiDAR and field plots to map the distribution of live and dead tree carbon in the Cameron Valley. I'm quantifying the influence of topography and riparian buffers on the rates of vegetation regeneration and tree fall within the valley floor. My study will contribute to the understanding of montane ecosystem recovery trajectories following severe wildfires.
Here we see close-up LiDAR surface models of the Cameron Valley floor where most of Jesse's ecosystem recovery and stem deadfall monitoring is focused. Field data are used to calibrate LiDAR models and then scale up to the entire valley. For example, field observations of stem count and deadfall are used to corroborate LiDAR maps of stem loss. Similarly, multispectral LiDAR imagery are being used to track new biomass growth, which is calibrated from plot measurements. Jesse is particularly interested to see if field-observed growth can be observed in either the active NDVI or NBR indices produced from multispectral LiDAR. At each of the field plots set up by Dr. Laura Chasma, Jesse is collecting height, cover, and photo-based indices of vegetation greenness. Results from 2018 are favorable, showing some correlation between plot-based greenness and LiDAR-based NDVI. 2019 and 2020 are yet to be processed, but so far it looks like multispectral LiDAR images will allow tracking of forest regeneration throughout the Cameron Valley. Okay, so now that we've explored some of our watershed monitoring innovations in the headwaters, let's travel downstream to where the prairies meets the foothills and check in with Danica to learn about her work with Piikani Nation.
My thesis synthesizes Piikani Nation's indigenous knowledge with remote sensing observations of their traditional lands. I'm using multispectral LiDAR to seek out culturally significant features and areas. Results from this project will provide a baseline for land use planning and environmental stewardship, as well as produce a 3D physical interactive map for community-wide knowledge dissemination.
It's early days in Danica's thesis and in our relationship building with Piikani Nation, but as a first step, we checked the available LiDAR archive for Alberta and found the Piikani Reserve lands had not been surveyed. Therefore, this summer we flew our multispectral LiDAR over the polygons shown here in red. So let's take a closer look at the floodplain area that we know is of cultural and historical importance to the community. As you can see, a LiDAR point cloud contains many structural and image-based attributes, but with the multispectral LiDAR we are most interested in the 3 intensity channels, from channel 1 in the shortwave infrared, channel 2 the near infrared, and channel 3 in green. Danica will use these data and community interviews for digital archaeolandscape mapping, the end goal being the co-creation of both online and physical 3D interactive maps to record and disseminate a cultural landscape history of these Piikani lands. Well, that concludes our whirlwind tour of my lab's research and innovations in the Upper Oldman Drainage Basin. So let's take stock of what we have learned and where we hope to go next. As you've seen, a common element in all of these studies has been the fusion of airborne remote sensing with boots-on-the-ground observations. And we've learned a lot about the dynamics of our headwaters and the innovative ways that we can monitor them. Our primary take-home message regarding headwater dynamics is that treeline can simultaneously advance, upslope, or retreat depending on aspect-based moisture limitations. This has important implications for future water resources, because treeline is the dominant watershed scale control on snowpack, both during accumulation and melt periods. We are also discovering and implementing new approaches, both for multispectral LiDAR and UAV-based headwater monitoring. However, the real innovations are the fusion of these technologies with machine and deep learning frameworks for efficient inventory of post-fire tree stems or for regional snowpack sampling and imputation. So, where do we hope to go now? Well, we still have a lot to learn about the post-Keno fire montane ecosystem recovery, so we're keenly interested in getting a handle on the valley floor and hill slope snowpack to forest cover feedbacks and their associated impacts on the downstream water resource. And finally, an area of growing activity and need is the fusion of geospatial data with community knowledge and capacity. We're currently using these approaches to co-create a holistic understanding of landscape physico-cultural dynamics with Piikani Nation. And we see this as a potential model for future Guardian-style stewardship within our shared headwater environments. So, thank you for your attention, and I do hope that our presentation has been informative. Bye for now.
All right. Certainly thanks to the 3 speakers, and Chris in particular, thanks for taking us back out into the forest and the headwaters, a day where I'm looking outside at a fairly dull, snowy, gray day in Edmonton here. So certainly appreciated all those presentations. So this is our chance for some questions and answers. So I'll point out to the speakers, you can look in the Q&A box, and Alex in the background has been organizing these where they're applicable into some folders, and so I'm going to go through and ask some of these questions of you and sort of engage in a bit of a dialogue. And I have a few questions myself if I need to use them before we wrap this up. So by starting with the order, I'll just go back to you, Rich, and just remind everyone when I'm asking you the question to unmute before you start speaking. So a question that's maybe something you can speak on. It's not specifically on the results, but it's the ability of maybe to take some of your learnings and knowledge from the results to think about potential future land use change in the province and its impact on land cover. And so just going to push this one to the desktop, and the question is there an adequate assessment framework in Alberta to evaluate the potential impact of mining in these alpine areas? And so you focused on, Rich, in particular, the sort of alpine hydrology impacts on downstream. And so The question here is a bit of a policy framework that, maybe you can't answer, but what you potentially could from the work that you've done to date and potentially knowledge of impacts of the geology as a result of mining. Can you sort of speculate what the potential impacts might be on water quantity or quality as a result of mining, recognizing there's been some change in policy in Alberta with respect to mining in the eastern slopes?
It's certainly a gap right now, I think, in terms of understanding the mining impacts and being able to model future scenarios that it would incorporate those impacts compared to what we know with forestry and other types of practices. So I think a direction that as a community we need of hydrologists where we need to go is to start to apply what we've been learning and approaches we've been taking in the assessment of these other industrial practices as well as disturbance impact studies and apply that to the mining world for sure.
Okay, all right. Thanks, Rich. I'm going to switch to a few questions that were directed towards Uldis right now. And we'll just push them to the desktop here. So Uldis, are the sediment loads that you represented under forest harvest conditions, were they normalized by flow? Because the comment is that as forest harvest was likely to increase flow. So was there a normalization of the data when you created the correlation that you had between the two?
Yes, absolutely. So two things, the sediment yield data, the concentration of sediment went down significantly. We did, however, see a moderate increase in stream flow. And so the data you were looking at is the normalized, the flow normalized sediment yield. So it's the overall production of sediment normalized by flow.
Okay, thank you, Uldis. Just waiting for the next one to load up here. So was the timing of discharge from logging notice? So did you see an effect from logging land cover change in the context of the timing of flows, as opposed to the quality, which you sort of emphasized in some of the results?
Yeah. And then, sure, and we didn't, I only reported kind of that really high level kind of integrated story. So yes, absolutely. Like so many previous studies, and Rich alluded to the same modeling result from the Marmot Creek work, that we're seeing an increase in early season flows. So we're seeing an advance of the timing of the melt freshet, not by as long as the models Rich suggested projected, but certainly by 10 to 14 days in advance in the onset of the timing of the melt freshet, and then an earlier sort of decline in those flows. The other part of that, was there an impact, for instance, on fish habitat connectivity or insect emergence? That latter part of that question really is probably more connected to some of the integrated water quality pieces. The key driver there in terms of aquatic ecosystem dynamics is going to be nutrients like phosphorus, which are really the limiting nutrients. No change in water temperature whatsoever. And phosphorus production actually went down. So there was no effect whatsoever on algal productivity. And it really is that algal productivity that would drive the macroinvertebrate population work. So really no effect on any of those aquatic ecosystem indicators.
Okay, thanks, Uldis. Have a couple more, and then I'm going to switch to Chris here. So question is, and you can, if you want, you can refer to the intent for publications. Is it possible to know who and how the data was collected that shows less impact after harvesting? And specific in terms of the sedimentation, I think, and the phosphorus and the organic carbon, as you presented there, because there was less on the quantity side. So just a reference of, if you can point to maybe where this material, the details of the science are going to be found in terms of publications.
Okay, yeah. So that work from the harvesting study, or the contemporary harvesting study, we're still in the process of evaluating a lot of that work. We're now at the stage where the story regarding the water quality impacts is becoming pretty darn clear. And so that work, we're just going to be beginning the publication of that work. It really doesn't do justice to try and publish some of the early interim results, but at this stage, we've got enough results that there's a pretty conclusive story. And so the publications on some of the work, the process work, showing limited to no erosion off cuplocks and stuff, that stuff has already been published. There's one particular paper in Journal of Hydrology. There's another piece that's in work that's focusing on the road stream crossings and showing the no impact of the 3 road stream crossings in those particular catchment studies. So that work is already underway in terms of being published. And the catchment scale results, that's work that we're going to be submitting for publication this coming year. And because of the time it takes for that material to go through the review process, we probably won't expect to see that publication in print for, perhaps 8 months to perhaps, 10 months. So the answer is that work is the harvesting study work is just starting to be published. There's actually a long stream of publications that need to come out as really spanning that whole breadth of hydrologic impacts, water quality impacts, ecosystem impacts, and downstream impacts. So that transdisciplinary approach also generates a really rich set of data that takes a long time to publish. So the quick answer is nothing yet, but oh no, I shouldn't say that. Some initial stuff has been published, but there's a lot that's going to be coming out in the next year or two.
Yeah. Okay. Yeah. Thank you, Uldis. And I'll just, Maureen, since you asked the question, you can always reach out to me, and we're just a couple months shy of. We always give the applicants that receive money from us opportunity after they submit a final report to us, a period of time before we make the report that they give us to being available. And so Uldis's report that he gave to us is a few months shy of being available too. So there's a potential source of information that you can get specifically from us. And I just sort of like to highlight that in the context of the question there, that one of the things that Uldis emphasized was, it was contemporary best practices. And certainly when you look at some historic context of harvesting, that you see the impacts were certainly greater in the past than application of best practices today, which is where we're liking to see the science provide guidance to. So I'll just push one more here and then switch to a few questions for Chris. And so Uldis, just wondering how it's possible or feasible to examine your approach, the forest management, sediment transport in other regions. And so, the context, maybe you could highlight the fact that the results maybe that you're finding from the eastern slopes and the Rockies in Alberta have been different from maybe some other geographies. And so it's important that you can't just take science that's developed elsewhere and replicate the results and put them into practices here. So it follows up with, do you think setting up a precise detailed model of the area to explore the potential reasons for some of the contrasting results? So the contrasting results that you had, respecting what you thought might be the outcomes from the hypotheses that you had at the start of this, respecting the harvesting.
Okay, so a couple of different things. On the first part of the question, 2 pieces here. There is more contemporary research just in the last couple of years that is showing similar kind of high-level outcomes where people are have looked at more contemporary harvest practices and best management practices in other hydroclimatic regions, Pacific Northwest, and so on. And so that narrative of best management practices being effective is not a new narrative. In fact, this work really only builds on it, and perhaps the most unique result here was the bizarre outcome that water quality actually improved after logging. But the comment in terms of the hydroclimatic region, Alberta Rockies are particularly unique because of our sedimentary setting, which is largely fine-grained sediments and then a glaciated history. So there's ample availability of fine-grained sediments at the surface. That means the disturbance effects on sediment and contaminants that are associated with sediments like phosphorus and some others behave very, very differently in Alberta than many other places. So that speaks to things like watershed recovery. So for an example, many places after wildfire, they see fairly quick recovery. And by quick, I mean 3, 4, 5 years in many of these water quality metrics. In Alberta, we are not seeing that quick recovery, and it's because of our geology and the ample supply of sediment. So it is important to keep that hydrogeologic context in mind. So we cannot generalize, work done in Australia or work done in the western states of the U.S. doesn't necessarily, isn't directly transferable. So, our situation is unique in that regard. The modeling, I'm even thinking about modeling these kind of contrasting impacts. Certainly, Rich showed some initial modeling result from contrasting disturbance impacts on flow. But it's an entirely different story when it comes to trying to project those impacts on water quality, aquatic ecosystems, or that broader suite of pieces. So really, this is just something I think that we're at the beginning of really starting to explore what is the real impact, the likelihood of these compound natural disturbances or natural anthropogenic disturbances. Because as I said, I think with intensification of weather and the shifting disturbance regimes, these compound impacts are likely to be much more frequent. And to our knowledge, we're the only study. No, there's one other study that tried to actually document some of those impacts. So this is a really emerging area of research, and it's actually quite stunning to sort of look at some of those impacts.
Okay, thank you, Uldis. Chris, I'm going to move to you now. I have one very explicitly to you, and then one I'm going to give you the option to open, and then I think it's one that touches on everyone's research. So Chris, question from Nessa, somebody you know quite well, Nessa Illich. Is there a component that links the snow cover surveys and efforts to estimate the depth of snow cover with the amount of spring runoff in the Old Man? So, in particular, the work that you've done, sort of enhancing our ability to do snow surveys, and then sort of link that information to volumes in the Old Man River or the Old Man Dam in particular.
Yeah, thanks, Brett. And also thanks, Nessa. Thanks for that question. Very relevant. Of course, most hydrological models follow the precipitation gradient, which suggests that snowpack should continue to increase with altitude. But of course, our observational data show that that's not the case. So it's a very logical question to ask whether or not we've implemented those observational data in our models. Well, actually, that was the subject of our proposal last year. So as yet, we haven't done that. But that is something that we would like to do. As some people may know, Steph Kienzl has been running his ACRU model to look at inputs into the Old Man Dam. And so one of the questions we would have is whether or not those model simulations will be sensitive to this new information about the snowpack distributions. Because it's not just a matter of where the snow accumulates, it's where does it melt from as the isotherm moves upwards. And I've discussed this with Pomeroy as well in the past, and I'm kind of curious to see how sensitive the model simulations are, because my understanding is most of our models are set up incorrectly, and we do need to adjust that.
Okay,
that's all
thank you, Chris. Yeah, thank you, Chris. So I had one I was going to ask, but this one puts it in a slightly different way. And it was, mine was going to sort of step back to sort of the basis of natural disturbance-based management and thinking how that was a paradigm to try to model forestry and some of the forest management practices in the past, thinking we would result in potential intended better outcomes. But there's an issue of climate change affecting disturbance regimes, and disturbance intensity that maybe makes us rethink some of the the philosophy for approaching management in the context of natural disturbance, whether it's fire or insects. And you all touched on this a little bit. So just to paraphrase this question, so by saying natural disturbance has been causing the greatest impacts and threats to source water, it sort of takes anthropogenic and human activities out of the equation, but there's obviously a link between those two in the sense of our natural disturbance regimes are now being influenced by anthropogenic activities in a number of ways. So I would argue, not me, that climate change is increasing the intensity and severity of natural disturbance, such as flooding and wildfire, and we should not be comparing two separate categories of natural versus anthropogenic per se, but rather events that are sometimes compounded events that pose the greatest risks and impacts to water quality or quantity. And so, the context that natural disturbance is now something fundamentally impacted on by human activities, and then the question of comparing these two and how we have that conversation in terms of the results of science and our potential ability to manage. So, Chris, you had some great comments from your work on the Kino fire as an example that informed some of the video. So I wonder if you could just make a few comments on this to kick this one off.
Sure, yeah. Actually, I would like to refer to Castle as a good example where we've got compounded natural and anthropogenic disturbances. Of course, in 1936, we had the wildfire. There have been other fires and other fire risks. We've had trail disturbances. We've got a ski hill, recreational activities. And of course, all of that transposed on top of climatological changes that we are seeing. And so we're able to identify individual changes, but as to attributing their underlying causes, I think requires a more system science approach or a holistic approach where we acknowledge that all of these factors play a role, and what it is our job to do is to try to decouple them or decouple the individual influences. And so the overarching framework that would allow you to do that would be a system science approach, and which is not focused on one component in isolation, but to model and simulate all of the components in their entirety and run sensitivity analyses on each individual component. So there is a framework for that kind of analysis, and it fundamentally draws on system science.
Okay, thank you, Chris. Rich, sort of any comment from your experience working in the bow and just sort of addressing issues about land cover change, whether it was through fire harvesting or insects?
Yeah, I'd agree with what Chris just said, and that's sort of the approach that I think most are taking right now, at least from a modeling end of things, right? So once we're confident in that these different disturbance regimes can be, simulated accurately, then we can start to combine the interactions between them and do that sort of sensitivity analysis. And your point about the anthropogenic versus natural disturbances is a good one, in that our hands are in a lot of pots now in terms of disturbance factors. I think at least our point of view, generally when we talk about anthropogenic disturbance or human disturbances, it's direct and kind of immediate, boots or tires on the ground kind of disturbance. And so a lot of the simulations and some of the results I showed today, when we talked about anthropogenic disturbance, was more like building roads, harvesting trails, even, a lot of our work is done at a former ski resort as well. So those sorts of direct human impacts, but the line is going to get less clear, I think, as we go forward and looking at the interactions among some of these natural disturbances and more the human impacts, or the human impacts on the natural disturbances, and the impacts of those disturbances on our processes will have to somehow be quantified.
Okay, thank you. Hey, if Rich, Uldis, and Chris, if you're willing to stick around a little bit, we have a few more questions. I know we originally sort of scheduled an hour 30 for this, but if you have some more time, certainly I'd like to be able to go through a few more of these questions if we can do it efficiently and sort of get to some of the issues that still touched on our audience. So Uldis, question from Stu Root here. So could the unexpected decrease in sediment following harvesting reflect the release of ground cover and understory vegetation, which follows harvesting or fire? And so,
I mean, certainly some of the ground cover responds fairly quickly after harvesting, probably much more quickly than after wildfire, because you've got a rhizome bank, a seed bank that's particularly a rhizome bank there. So, you know, you get reestablishment of grass on those cut blocks fairly early. My instinct is, if this is from Stu, my real instinct is that a lot of what we saw, because you really have to ask yourself, how does sediment production go down? How could logging actually cause sediment production to go down? I could see logging producing limited to no impact on sediment. But really, because of the reclamation activities that were done as part of the harvesting, some of the road deactivation, reclamation work, what likely happened is that reclamation work actually pinched off sediment sources that had been present prior to the harvesting. You know, we have 9 years of pre-disturbance sediment and flow data and full suite water quality data. And what the data shows very, very clearly is after the harvesting, production of particulate contaminants, in particular sediment, phosphorus, a number of those very, very clearly went down. And so I think the most likely, and even though we can't pinpoint exactly which best management practices are implicated, what's clear is that probably pre-existing sediment sources were pinched off during the reclamation activities. I think that's far more likely the driver here, because the change was not subtle. The change was immediate.
Okay. Thank you, Uldis. Question from David Hill here. And so for those that don't know, in the past, David would have been both sitting in Vicky's chair, who normally has been moderating these, or my own chair in a capacity when he worked with Alberta Innovates before, and now is down at the University of Lethbridge. And so I'm wondering about how to leverage and synthesize these research findings and how it connects to downstream water supply and security. It's certainly pertinent as many are aware that there's plans and a lot of dollars looking for a significant expansion of irrigated agriculture, both in Alberta and in Saskatchewan. And so issues about land cover and land cover change and climate impacts on water supply are sort of critical to this. So, David, I'm not sure that it's a question to anyone in the audience in terms of the importance to leverage and synthesize these research findings. I'm wondering if I can try to answer this for everyone. We just went through a science review for our water innovation program and had a number of recommendations, 6 in particular, that come to mind. One of them focused on knowledge mobilization, and I'd like to suggest that there's a greater emphasis on Alberta Innovates to think about how we explicitly support knowledge mobilization, whether it's to ensure the sort of translation or movement of the science that comes from the individual researchers out into the community, or collectively a role that we can play is to support the synthesis products, where we provide a venue to bring sort of multiple projects together to synthesize the research to address some of these big questions. So just, to highlight, there's a role for knowledge mobilization and synthesis, and that Alberta Innovates can play a role in this. Anyone, I don't know if you want to explicitly comment on this question at all? I'll take it as maybe that I answered it. I'll just go on. So I got the yes from those that are managing the platform for us, that we can run this for a few more minutes. And so a question, these are very interesting presentations with explorations of different aspects of Rocky Mountain hydrology. How much coordination or overlap is there across the studies? And so I don't know that you can necessarily answer that. How about I answer this? if it's relevant from an organization as Alberta Innovates that has played a role in funding and sustaining components of these 3 programs, is we certainly saw them and see them as complementary and additive. And you'll see from Rich's presentation that had certainly a bit more emphasis on the climate land cover interactions, with a greater emphasis on some of the modeling that touched on water quantity and less so on the quality per se. Uldis's work that kicked off back in just post 2003 wildfire in the Upper Oldman has really started with a focus on impacts on water quality in particular, and in doing so always had elements that needed to address issues about land cover impacts, initially on wildfire, but then moved to forest harvesting explicitly to address the issues on water quality change and impacts on source water from a protection perspective. And then Chris has been certainly doing work that's a bit of a hybrid approach, and then with a greater emphasis on innovative remote sensing technologies that can look at land cover change and those impacts on hydrology. So from our perspective, they didn't overlap except in areas that, I would argue that it's important that they do overlap, because you need replication, and the replication was occurring across 3 watersheds to provide greater power to the conclusions. Uldis, Rich, and Chris, do you have any comments on that? I'm not sure that they were asking me to answer this, but is there anything that you want to add on?
I'd like to say something. Uldis, Rich, and I know each other quite well, and we're not overlapping. We're trying to make sure that that our work is synergistic. So I don't think there is any overlap. I think it's all highly complementary work.
Yeah. Okay. Well, I'll take that as the nod from all 3. So thanks that. I'm just going to move to a question from Monterey. Thanks to all the presenters. I guess my question is general, and that given the importance of the region and the technological advancements, is there any initiative to monitor and provide high-resolution data for regional studies in mountain regions for examining different methods and approaches by a wider research community? So any initiative to monitor or to provide high-resolution data in mountain regions to support a broader research community. So it's kind of linking, whether it's the monitoring or the data component, that can then link to some broader hydrological, regional, land use, land cover, water studies. Anyone have any comments on that?
I have a
Chris?
related comment. I think what is being requested there is very broad and requires some high-level strategic oversight. But here in the south, in particular the headwaters of the Oldman, one initiative we're trying to move forwards is what we would like to term the Headwaters Institute. And so it would be led out of the university, and it's intended to be multi-stakeholder, impartial, objective, provide a forum for knowledge and data sharing for all stakeholders in the headwaters. We haven't started this yet, but it's an outgrowth of our many years of activity in the headwaters. And so it could play a role in disseminating knowledge, perhaps a node for data, but it isn't intended to be a data node. However, that's the kind of thing we could take on, is try to facilitate this kind of sharing of knowledge and information, and just provide a forum to address these kinds of challenges if they're needed.
Okay. Thank you, Chris. I've got one other question I might push here, and then we'll wrap it up. And apparently it's nicer in Leduc. So question from Kevin Kemble here from Nate Boyle Research Institute. So this is for Richard. Thanks for the presentation. Depending on what prediction you look at is the fire regime that will change the most. And so are you able to look at fire severity and interval like you have for harvesting in the model, where you specifically looked at sort of comparing some of those potential future scenarios where you ran the harvesting and fire or mountain pine beetle.
The short answer is not yet. I believe John Pomeroy and his group in the Cold Water Lab in Canmore have somebody coming on now in terms of a new grad student who's going to be looking at some of that stuff. But it is an important aspect of that disturbance regime that we need to look at and test from a modeling point of view, because certainly the change in frequency and intensity with a changing climate is going to be key. And as our results show so far, that is, one of the main impacts that has the greatest effect on yield. So it's something that we do have to move into, but we don't have any of that done at this time.
And so I guess, thank you, Rich. I think we'll close it off now. There's one or two other questions here. I can answer those individually because they just had some explicit. So if you stay on and look at the chat box, I can add some answers to those. So with that, I'd just like to sort of wrap up with a few closing comments, and certainly for one, this is an area that's passionate and interesting to me, and so I appreciate the three presentations that we had today. And from a water innovation program perspective, it's always a challenge to support research and innovation dollars for watershed scale research. And I know you're all faced this challenge because both the scale over which you have to try to practice your research, both in space, but in particular in time. And because we all live in a cold water climate in Alberta, that when we're looking at land cover change, responses or the restoration, reforestation things happen long after. And so, the intent to invest has to be for the long term before we actually see the reward from the science results that can help us in terms of development of best practices and so on. So I appreciate the work that you're doing. Just to reach out to the audience, I'd like to thank everyone for attending today's session, and I hope the discussion sparks some new ideas for you. Just for your benefit, so that you know, the session is being recorded or was recorded, and we post these recordings on our website, and it'll be done so in the next week. We'll be sending out a short survey after the session to those that did connect, and so your feedback is certainly welcome, and it helps provide us content for how we can manage this program in the future. So our next session on municipal water management in a changing world will be held on November 18th. The full schedule can be found by clicking on the schedule button that you can see in the top right corner of your screen right now. We certainly look forward to connecting with you all again, and I'd like to say thanks to Chris, Uldis, and Rich for joining us today, and thanks to the audience for connecting with us. So have a great Thursday, everyone.